Yeah, we are absolutely delighted that today we have Elena, who's going to tell about photocathode characterization techniques, which is by popular request of all of you. So we're really happy about that. After Elena, we are going to have a very interesting video. And we had other requests also for other topics like SRF characterization, and we will get to that. We have heard that and will respond, but it will be at a different time. So, thank you, Elena.
Sure. Good morning, everyone. My name is Elena Echeverria, and as Richie said, I will be talking about briefly about some characterization techniques that we use to characterize, obviously, the cathodes that we grow in our lab. This is the overview of the talk. I will give a brief introduction, and then I choose these 4 characterization techniques. They are not the only ones, but those are the most used, at least in our lab in Phoebe. Okay, let's start with the intro. You have heard a lot about brightness, right? And in this expression here, I'm just showing you the definition for the normalized brightness. And what I want to highlight from this expression are these 2 terms. The first one is the beam current, and the beam current is related to the quantum efficiency of the photocathode, the laser fluency, and the lifetime. And the second one is MTE, which stands for mean transfer energy. And this is also related to intrinsic momentum spread of the photoelectrons that we are generating. It depends on the roughness of the sample and also laser heating. Of course, if we want to have a bright beam, which is mainly the goal of this center, we want to have samples that have high current and low MT. And this is basically the goal of the team 1. So we focus on having photocathodes with high quantum efficiency and low MT. How can we do that? Well, first let's talk about the quantum efficiency. The definition for external quantum efficiency is written here. Is basically the current that we are generated divided by the incident photons. This is basically how efficient is the photocathode in receiving some light and producing some electrons or current. So the highest the number of electrons the photocathode is producing with the same amount of light, the high quantum efficiency we will have. How can we achieve this goal? Well, there are different candidates. The most known and the ones that have shown highest quantum efficiency are alkali or bi-alkali antimony thin films. Among them, we have cesium-3 antimony, potassium-cesium antimony, sodium-potassium antimony, and so on. Those are popular because they have shown to have really high quantum efficiency. Now, what about MTE? Again, MTE, you can think about the momentum of the electrons, right? And we want that momentum of the electrons to be perpendicular to the sample. We don't want electrons going in different directions because that will increase the MTE of the sample. In this cartoon here on the left, we have a photocathode with electrons that are going in different directions. That photocathode will have a high MTE, while on the other side, we have a photocathode with most of the electrons going perpendicular to the surface of the photocathode. That photocathode will have low MTE. How can we achieve low MTE on our photocathodes? Well, one solution is to grow films that are flat and ordered. Okay? The idea behind that is that you won't have too much scattering when the electrons are going out, and therefore the electrons can go perpendicular to the sample. How can we achieve both high quantum efficiency and low MTE? Well, one way is using a deposition system that is called molecular beam epitaxy. In this slide on the right, you see a cartoon of the process. Basically, in this example, I have cesium and antimony. And the reason because this is called molecular beam is because the sources are going as a beam. They go into the substrate where we want to deposit the film as a beam. So the atoms are deposited in this way. We also have a heater. We can change the temperature of the substrate to achieve high quantum efficiencies. And also, we can measure the quantum efficiency in situ, and we can have RHEED to look at the crystallinity structure of the sample. I will be talking about more about those techniques later. Now, the samples that we will be growing are thin films. The thickness is about 10 nanometers. And this technique allows us to grow these thin films and also to have a better control of the samples. Okay? So this is basically the main point of this. Now, how can we know what we are growing, right? This is a nice system to grow samples, but how do we know what we are growing? Then we have to characterize the samples, right? One way or one technique that is used a lot is looking at the quantum efficiency of the photocathodes. How do we do that? Well, I already showed the definition of the external quantum efficiency. And what we do is while we are growing the samples, we monitor the current that is generated. For instance, if we have a fixed incident photons, we only need to monitor the current that is being generated. In this example here, which is a plot taken from this article, they are showing the photocurrent of the cathode that they are growing in red and the temperature of the sample on green. This example is for a sequential deposition of antimony, potassium, and cesium. And the idea behind that is that we will change, or people will change, certain parameters of this during the growth, like temperatures or fluxes, in order to have the highest quantum efficiency. For instance, we know that antimony is not a good emitter in green. Therefore, after depositing some layer of antimony, we don't see any photocurrent. Then they open the shuttle of the potassium, and they wait until the quantum efficiency goes up. When it starts going down, they close the potassium and they decrease the temperature, as shown here, to start depositing the cesium. Once they start depositing the cesium, the quantum efficiency will go up, and they will wait until they have the highest quantum efficiency to stop the growth. Okay? So this is one of the most used techniques when we are growing photocathodes. What else can we do? We can also look at the spectral response. The spectral response is basically the quantum efficiency as a function of the wavelength. Now, instead of having a fixed laser, a fixed wavelength, we are changing the wavelength and we are looking at the quantum efficiency for each wavelength. Why this is interesting or important? Well, first is telling us what is the limit of the emission for each photocathode, but also if you look at this plot, there are three different trends, and this is for cesium antimony cathodes. What I want to highlight from this plot is that the black line is for cesium-3, while the bluish ones are for cesium-1. So by just looking at the spectral response of the photocathode, we can distinguish if we are growing cesium-3 or cesium-1 cathodes. Now, the ones in between are mixed phases. We don't know exactly what we are growing, but at least we know it's not pure cesium-3 or pure cesium-1. What else can be done with the quantum efficiency? We can do oxidation experiments. We know that the cathodes, they are really, really sensitive to air, okay, or oxygen. And we can dose the photocathodes in a controlled manner with oxygen and see how long they live, okay? And this is what is shown in this plot. This is the normalized quantum efficiency as a function of the oxygen dose, and we are looking at when the diode die, the photocathode die. The blue curves are for two different cesium-1s. The red one is for cesium-3, and the green one is cesium potassium antimony. And here we can see why people is interested in cesium-1. We are interested in cesium-1 because it has really high resistance to oxidation compared to cesium-3. Cesium-3 can live a little bit or die immediately after being exposed to oxygen, but cesium-1 will last longer. Also, you can see from this plot that if we include potassium, we will have a little bit more response respect to cesium-3. Okay, those are the kind of experiments we can do and the characterization we can do on the cathodes in terms of quantum efficiency. What else can we do? We can look at the RHEED. RHEED stands for reflection high energy electron diffraction. And basically, this technique helps us to look at the crystal structure of the cathodes that we are growing. This cartoon here shows the setup. It's a really simple setup. We have an electron gun, the film that we want to analyze, and a fluorescence screen. Now, once the electron beam hits the film, it will be diffracted, and the diffraction pattern can be seen in the screen. And by looking at this diffraction pattern, we can recognize or distinguish what kind of films we are growing. Something I want to highlight from this technique is that it's really surface sensitive, and I will show you in a minute why I'm saying that. Here we have, let's imagine that we have a lattice with certain parameters. This is the real space of this lattice. Then if we take the reciprocal space, we will have basically rods going in this direction. And if we have the electron beam coming in this direction, again, it will be diffracted, and we can look at the diffraction pattern in the screen. Now, if we analyze this diffraction pattern, somehow we can go back and know what kind of crystal structure we have. But also, I mentioned that this is surface sensitive, right? This is the reason. So we will have different diffraction patterns depending on how is the surface of the photocathode. If we have a photocathode that is flat and single crystal, we will see the reciprocal space will be rods, really thin rods, and the pattern in the RHEED will be spots. Now, if we have a flat surface with small domains, those rods on the reciprocal space will be thicker, and therefore we will see streaks on the RHEED pattern, and so on. So we can, by just looking at the pattern of the RHEED, we can get an idea of how rough or how nice is our film on the surface. And here I have few examples. Sorry, probably the labels are not easy to see, but here are few examples of RHEED images that we have taken in our lab. This is for cesium-1, so we see streaks, meaning that it's an ordered film. The bottom one is for antimony. I mentioned before that antimony is not a good emitter, so how do we know that we are really growing antimony if we are just looking at the quantum efficiency? We cannot, but we can look at the RHEED, and antimony should show rings because this is polycrystalline. Now, the fact that you have spotty rings here means that that film is not only polycrystalline, but is also rough. So we have some roughness on the surface of this sample. And now the most important and interesting part is the cesium-3. So these images are from the single crystal cesium-3, and it was the first time that it was here at CBB when they discovered for the first time this, or they grow for the first time this single crystal. Now, it will have also some streaks, but if you change the angle, you will be able to recognize the different orientations of that crystal. And again, by just looking at the spacing or the geometry of those patterns, you can go back and get some information about the crystallinity of the photocathodes that you are growing. Sorry. Okay, what else we can do? We can do XPS. What is XPS? XPS is X-ray photoemission. This cartoon is not only for XPS, but in general for photoemission spectroscopy. Photoemission spectroscopy is based on photoelectric effect. We have a light coming in, interacting with the electrons on the surface. Those photons will give enough energy to the photoelectrons such that those electrons will be kicked out from the sample, and they will be read by the analyzer. The setup is very simple. We need a source of the light. Again, if we are using X-rays, we will call it XPS. We need the sample. The sample can be rotated and different information will be obtained. And we need an analyzer, and the analyzer will be reading the kinetic energy of those photoelectrons. Why do we need to read the kinetic energy? Well, this is cartoon of the energy levels for the electrons. If we have the photon can interact in principle with any electron in the surface or in the atom, and it will provide enough energy that that electron will be removed. It will break the bond between the nucleus and the electron. And that bond is what we call the binding energy. Once the electron is free, it will move and it will reach the analyzer. Let's think about conservation of energy. If we have the energy of the photon, that energy will be used for what? First, we need to break this bond. We need to break the bond between the nucleus and the electron. And that's, again, binding energy. Once this electron is free, it needs to reach the analyzer, and this is what we call the work function of the system. And we can calibrate each system and know what is that value. So this is going to be a fixed value. And whatever energy is left will be read in terms of kinetic energy. So if the analyzer is reading the kinetic energy, we know the kind of photons that we are using, and we know the work function of our system, we will know the binding energy of the electrons. The typical plots we will be seeing are like this one. Basically, we will have plots that are intensity as a function of binding energy. That intensity is related with the number of electrons in that particular energy level. And I already mentioned what is binding energy. The survey scans will help us to distinguish which elements we have on the surface of the sample. On this example, we only have carbon, and on the bottom, we have a sample with more elements, okay? And something I want to highlight from this is that by looking at this is a sample that was grown on silicon, and here we can see the peaks of the silicon. If we can see the peaks of the silicon, it means that probably the sample is less than 10 nanometer thick. Now, what else can we know besides of the element and composition of the sample? We can also get information about the bonding environment of these elements. For instance, again, on the top we have graphene. The binding energy for the carbon is 284.4, while the binding energy for the second sample is 286.5. So that shift in binding energy is telling us that the carbon is oxidized or is bound with a different element. And we know this is going to be carbon-carbon, and this is probably carbon oxide. Now, the oxygen. Here, we can say that this sample is really clean because the peak for the oxygen is really small. It's about the noise of the data. But here, the peak is considerable. So we can say this is either oxidized or there is some contamination of oxygen. Now, how can we use this technique to gather some information about our photocathodes? Well, here is an example for cesium-3 versus cesium-1 antimony. The blue one is the peak for the antimony 3D, and the black one is for cesium-3. First thing that you want to notice is that there is a shift in binding energy, again, meaning that there is a different oxidation for the antimony. But also something I want to highlight is that here we have few peaks on the black curve that the blue one doesn't have. Those peaks are related with oxygen. And the fact that the blue one doesn't have those peaks is also an indication that that sample is really robust to oxygen. So it doesn't oxidize as easily as the cesium-3. Something else that we can do is we can change the angle between the analyzer and the sample, and therefore we will have more information about the top surface of the photocathode. Here I wrote bulk versus surface because, of course, it's not like we are looking at the bulk. XPS is just surface sensitive. We will look at the about 10 nanometers thick. But we can compare that in average, that thickness, compared to the most top layer. How do we do that? We change the angle and we analyze the data. Here we have three different samples. Those are the ones that I showed at the beginning that are mixed cesium-1 and cesium-3. And by just looking at and analyzing this data, we can know what is on top and if the sample is more cesium 1 than cesium 3. And for instance, here, if you look at the black line, most of the peaks corresponds to cesium 1. So we know that these samples are mostly cesium 1, but with some other mix on the top of the surface. Okay, what else can we do? We can look at the MTE, mean transfer energy. The mean transfer energy quantifies the angular spread of the electron beam coming off from the cathode. I already mentioned that if we want to have a cathode with really, really low MTE, what we want to do is to have all the electrons pointing in the same direction, but not only in the same direction, but also we want that direction to be perpendicular to the surface. And also, the MTE limits the brightness of the beam, along with the size of the laser that we are using to produce those photoelectrons. How is that? Well, that basically means that you cannot have, at least in a linear accelerator, you cannot have a brightness in the beam in the line that is higher than the brightness at the surface of the photocathode. So that is the highest brightness that we can have. Can we get better? Yes, we can do, can we get worse? Yes, we can do worse, but we cannot get anything better than the surface. And this is a setup in, here at Cornell. Basically, here we have the setup for measuring MTE. We have a gun, which is a DC gun, I think is 15 kilo electron volts. We have some solenoids and correcton coils, which will allows us to move the beam around to specific places where we want to have it. And we have the detector and some screens. How we measure the MTE? Well, we actually don't measure directly MTE. What we do is first we have to generate the beam. This is the beam generated from the photocathode that we want to study. We make that beam pass through this aperture, and then a new beam will be created. That beam will hit fluorescent screen, basically, a scintillator screen, sorry, and we can measure the momentum of that beam. Now, if we move around in X or Y the original beam here, we can get at the end a plot that is a phase space of that photocathode. And by looking at the phase space of the original photocathode, we can get information about the emittance. Why we need information about the emittance of the photocathode? Well, because using this expression, we can get information about the MTE. So from this expression and from the emittance, we can know what is the MTE of the sample. Now, this is the size of the laser that we are using to emit this beam. So that's why also before I said that we cannot get any brightness that is better than the, I said before that the MTE will limit the brightness because, and also the size of the laser. Okay, and with that, and here we have few examples of the kind of images that we will obtain for the MTE. These images were taken from the talk from William Lee in our group. And here what he was presenting is the MTE of a cesium-3 antimony cathode. So again, these are the phase space plots or images. From these plots, he can get the emittance for each component. And from that, he obtained the information about the MTE of the samples. Okay. And with that, I will summarize. I have presented 4 different, again, they are not the only techniques, but those are the most used in our lab. And we talk about the spectral response. I want to, again, highlight why we think that the spectral response is important. It's not only important because it will tell us the limit of the photoemission, but also I believe that if you don't have any other technique in your lab to look at the samples, you can just look at the spectral response, at least for cesium 3, and distinguish what kind of cathode you are growing. There are different labs that only have quantum efficiency measurements, and they don't know if they are growing cesium 1, cesium 3. So by just looking at the spectral response, they can get an idea of if the sample is pure cesium 3 or pure cesium 1. Now, how about the samples in the middle? Well, then we need another technique, right, to characterize them. And this technique is, could be XPS. XPS will help us not only to distinguish the elements that we have in our samples, but also the bonding environment for each element. We have RHEED that will help us to know the crystallinity of the samples. And in our case, for CBB, this technique helped us to see that we were growing for the first time a single crystal cathode that is cesium 3. And also, MT measurements will tell us how good is our cathode in emitting these photoelectrons. And with that, I want to take any questions. This is Jared's logo, by the way. This is the logo of our group. Okay, any questions?
I was just curious, a couple slides ago you had, or I mean there's more than a couple, towards the beginning you had the plots of the, I think it was, I don't remember if it was quantum efficiency, but it was like the lifetime where like the cesium 1, I think it was, was less, yeah, that one. It was quantum efficiency. I'm just wondering, when these plots end, is that just because like the data was stopping being taken, or does something like happen that like stops it from working?
It's just because we cannot read more the photocurrent. I mean, what we do here, we are plotting quantum efficiency as a function of the oxygen. But in reality, because we have a fixed laser that we are using to take the data, what we are monitoring is the photocurrent. Okay. So once we reach the limit of noise of the photocurrent, we stop taking data. At least for these two cathodes, it means they are gone, the samples are gone. In these cases, it's just because we were tired. It took us a lot of time, and we weren't seeing much change on the quantum efficiency. So we were like, okay, I think that day was like 7 p.m., and we were like, okay, that's good enough. Mm-hmm. And again, it doesn't seem to get any worse or better. And of course, if you wait long enough, probably it will go down at some point. But I think this was good enough. Mm-hmm. Yes?
I have a question on slide 18.
18?
Yeah. Oh, 80.
Sorry.
Yeah, so for the plots on the right-hand side, if I read the labels correctly, it is carbon 1s and carbon 1s, right? Okay. So by that, I'm assuming that the electron is getting excited from the carbon 1s orbital.
So the electrons, if you go here, here, the binding energy of, here, carbon will have an energy level similar to this one, and it has two levels. One is 1s, and the other one is the OJ peak. And this is the 1s.
How does the energy shift of the 1s orbital help you understand the bonding region? Because 1s electron don't participate in bonding, right?
So what your question is why we have the shift in the binding energy? Yeah. Well, if you think about, again, this energy level, right? If you have an atom that is bonded carbon to carbon, that binding energy will be different. So to break that bond, you have to break the bond between the electron and the nucleus on a carbon-carbon bond. That energy will be different compared if you have carbon and oxygen.
But that's true for the valence electrons, right? But not for the core electrons. Core electrons are...
Well, it depends on the element. There are elements where the shift is really small that you cannot distinguish. But in the case of the carbon, it's really known that you can distinguish between the oxidation states. And yeah, again, that will depend on the element. And Melissa may have something to say. But here also you can see that it will depend on the oxidation.
Yeah, so that's a great question. So what XPS is measuring is the oxidation state. Okay?
Okay.
So it's essentially measuring the effective nuclear charge that the electron is in. And as you change the oxidation state, you change how strongly the electrons are bound to the nucleus.
Even for core electrons.
Yes, even for core electrons. Okay?
It's a
Because-
local
because-
electrostatic potential in DFT.
Okay.
If the atoms surrounded change by electrostatic potential at the carbon nucleus go up and down.
Okay.
That's what you see.
But
And
no,
SSS
the
is
electron
similar.
is not at one place. The
Yeah.
electron is delocalized. And so when you took general chemistry, we told you that there are quantized oxidation states. One of the really cool things to come out of XPS and to come out of electronic structure theory is that's really alive, okay? And so it turns out that for different bonds, you have different effective oxidation states, and it can be a very useful measure of understanding what the bonding is, even though, as you say, it's a core electron that is not participating in the bonding.
So in other words, all the core electrons, the whole atom moves up and down in the electrostatic potential because of the surrounding, because of that, because of that removing of charge, your valence charge, right? So in DFT you see that.
Yes. I have a question about slide 10, I think. Spectral response curves. Yeah. So does film thickness affect the spectral response curve? And if so, do you know that the film thickness was the same for all samples?
So the thickness affects somehow the spectral response. Depends also on the substrate. So for instance, we have seen oscillations on the spectral response for really thin films, okay? And also the quantum efficiency for can be different, but the trend is similar. So the quantum efficiency could be higher or lower, but the trend for the cesium 1 or the cesium 3 will be the same. But yes, the thickness may affect the quantum efficiency, but not the trend per se.
Do you know what was the thickness for those particular samples? And how do you estimate the thickness of cesium 3sb and cesium 1?
I don't remember the thickness of these samples, but I remember that we were trying to do about the same. So in terms of the fluxes that we are using and the time that we were doing the deposition. Now, how can we estimate the thickness? We can do it through, it's just an estimation because we cannot really measure thickness in this setup. But if you know the fluxes of the sources, you can get an estimate of, and you know how long you have been depositing, you can get an estimate of the thickness.
Typically, you monitor the thickness of antimony, not thickness.
Yeah, we monitor the rate.
And then multiply by some factor to get the thickness of cesium 3sb. But do you use the same technique as cesium 1? Because I guess this factor will be different.
Yeah, the factor will be different, and we haven't done much calculations for the cesium 1.
So this is for slide 7. Why do you guys grow the film on silicon? Is that like a known substrate?
Yeah, we have grown samples on silicon, just pure silicon. But the reason we are using silicon carbide is because it has, we want to grow single crystal, cesium 3, and it has a lattice match with silicon carbide. But in principle, graphene will help as well. Silicon nitride also has a good matching with one of the orientations for the cesium 3. So in principle, and this technique will help in principle for any substrate, but what you have to keep in mind is what are the fluxes and the temperatures that you want to use for the graphene. Yes?
Something I wonder about these cathodes, because I'm going to be the one testing them. Do we ever think about incident fluence? Because I imagine, we're focusing a laser down to a small size, so we can get high fluence, do I have to be afraid of damaging them and affecting surface, like introducing more roughness?
If you are using, for instance, even the electron gun from the RHEED can damage the surface of the electrons, of the photocathode. So yes and no. Of course, we have to worry about those, but depends on the kind of information that you want to gather, right? If we are just looking at if you want to see if you are able to grow a single crystal, right? Of course, you need to have a really, really nice film. So you try not to look at the film with the RHEED or just have a power laser pointing to the sample, because that may affect the growth. So you do the best that you can, but sometimes it's really, really hard.
So these are awesome questions, and if you have more, ask them to Elena during the break. Thank you again.